It's really the government that is behind this, looking for alternative power sources now that the nuclear power is taking a much smaller role in Japan. And it's all kinds of ways of using hydrogen, including perhaps using it as a fuel in power plants. That's more distant in the future, but even later this year, early next year, Toyota is supposed to start selling cars that are powered by fuel cells, which in turn are powered by hydrogen.
Japan has just created a new type of rechargeable battery that could change the direction of the global electric vehicle industry. It stores energy using hydrogen and magnesium instead of placing lithium at the center of the system. Inside the battery, hydrogen ions move through a solid material, producing electricity while also storing hydrogen in a safer and more compact form. The Japanese cell reached 2030 milliamp-hours per gram, matching the full theoretical capacity of magnesium hydride. It also operated at approximately 90 degrees Celsius, far below the extreme temperatures normally associated with magnesium-hydrogen storage. This discovery arrives at the exact moment China dominates the global lithium battery industry. Chinese factories control battery cells, cathodes, anodes, mineral processing, and some of the cheapest electric cars in the world. But Japan has now opened a route that does not begin with lithium, and China's response is already visible. Chinese researchers have developed their own hydride ion batteries, followed by a magnesium-hydrogen prototype that operates across a wider temperature range. The competition has moved from lithium batteries into an entirely new field. If China learns to manufacture this technology as cheaply as it manufactures today's electric cars, hydrogen EVs could eventually enter the same price range as China's smallest city vehicles, possibly approaching $6,000. So what exactly did Japan build? Why is it different from every normal EV battery? And why is China moving so quickly to develop the same technology? The breakthrough came from researchers at the Institute of Science Tokyo, working with several major Japanese research organizations. Their device is known as a magnesium-hydrogen battery, or an Mg-H2 cell. Instead of moving lithium ions between two conventional electrodes, the Japanese battery moves negatively charged hydrogen ions known as hydride ions. On one side of the battery sits magnesium and magnesium hydride. On the opposite side sits hydrogen gas. Between them is a solid electrolyte designed specifically to transport hydride ions while keeping the two sides separated. During discharge, hydrogen gas receives electrons and becomes negatively charged hydrogen. These hydride ions move through the solid electrolyte toward the magnesium side. When they reach the magnesium, they form magnesium hydride. At the same time, electrons move through the external circuit, producing usable electrical power. During charging, electricity reverses the reaction. The magnesium hydride separates. Hydrogen ions move back through the electrolyte and return to hydrogen gas on the opposite side. The same hydrogen can therefore move forward during discharge and backward during charging. This is what makes the device rechargeable. It is also what separates it from an ordinary hydrogen storage material. The Japanese cell does not simply hold hydrogen and wait for extreme heat to release it. Electricity controls when hydrogen enters the magnesium and when it leaves. That allows the battery to perform two connected functions. It stores hydrogen inside magnesium hydride, and it produces electricity through the same reversible reaction. The strongest result was the cell's measured capacity. The Japanese team reached approximately 2030 milliamp-hours per gram, which matched the full theoretical capacity of magnesium hydride. That means the reaction successfully used nearly all the hydrogen available inside the active material. The magnesium hydride also held approximately 7.6% hydrogen by weight. This gives the chemistry an unusually high active material capacity compared with many conventional battery materials. But the most important progress involved temperature. Magnesium hydride has always been attractive because it can store a large amount of hydrogen inside a solid. The major problem is that releasing that hydrogen normally requires enormous amounts of heat. Traditional magnesium hydride systems can require temperatures between approximately 300 and 400 degrees Celsius. Japan's new electrochemical system performed the reversible reaction at approximately 90 degrees Celsius. That is still hot, but it is a major reduction. The Japanese researchers did not merely improve the material slightly, they changed the method used to move the hydrogen. Instead of relying almost entirely on heat, the cell uses an electrical reaction and a solid hydride ion pathway. That is the foundation of the breakthrough. Japan built a rechargeable battery where hydrogen itself carries the reaction, magnesium stores it, and lithium is no longer required at the center of the cell. Why removing lithium matters. Almost every modern electric car depends on lithium-ion batteries. Lithium ions move between the battery's electrodes while the vehicle charges and discharges. The system works extremely well. Lithium-ion batteries have improved in range, charging speed, safety, and price for more than 3 decades. But dependence on lithium also creates a powerful industrial chain. The battery requires lithium compounds, cathode materials, anode materials, separators, electrolytes, and highly specialized factories. A small number of countries control much of the processing and manufacturing required to produce these batteries at scale. China has built the strongest position. It does not only assemble electric cars. China processes battery, manufactures cathodes and anodes, produces battery cells, builds battery production equipment, and operates enormous recycling networks. That system allows companies such as CATL and BYD to produce batteries at prices that many foreign manufacturers struggle to match. Japan's hydrogen battery creates a different material route. Its central reaction uses hydrogen and magnesium. Its solid electrolyte contains materials including barium, calcium, sodium, and hydrogen. Lithium is not carrying charge through the main battery reaction. This creates the possibility of an energy storage industry that is not completely tied to the same lithium supply chain. Magnesium is especially important. It is widely available, already used across multiple industries, and capable of storing hydrogen inside magnesium hydride. A battery built around magnesium and hydrogen would require new factories and new production knowledge, but it would also create a new competitive map. Countries and companies that currently struggle to compete with China's lithium-ion scale could develop expertise in hydride ion conductors, solid hydrogen storage, and magnesium-based energy systems. This does not remove the value of lithium-ion batteries. Lithium batteries remain highly efficient for passenger cars, electronics, and many forms of grid storage. But Japan's discovery gives manufacturers another direction. The future EV market may contain several different battery systems instead of one dominant chemistry. Small city cars may continue using lithium iron phosphate batteries. Long-range passenger vehicles may use improved lithium, sodium-ion, or solid-state systems. Heavy trucks, trains, ships, and industrial machines may use hydrogen electric systems. Japan's magnesium-hydrogen battery could connect directly to that transport market. And the reason becomes clear when looking at hydrogen's biggest problem: the hydrogen storage problem. Hydrogen contains a large amount of energy for its weight. That makes it valuable for transportation systems requiring long-range, fast refueling, or heavy workloads. But hydrogen is extremely difficult to store. At normal pressure, hydrogen is a very light gas that occupies a large amount of space. A vehicle cannot carry enough low-pressure hydrogen for useful range without an enormous tank. The first solution is compression. Modern hydrogen passenger cars commonly store hydrogen at pressures approaching 700 bar. These tanks are made from advanced materials and surrounded by strong protective structures. They also need valves, pressure regulators, sensors, fuel lines, and emergency shutoff systems. The hydrogen is light, but the complete storage equipment adds weight, cost, and complexity. The second solution is liquid hydrogen. Hydrogen becomes liquid at approximately -253 degrees Celsius. In liquid form, it takes up far less space. But cooling hydrogen to this temperature requires large amounts of energy. The storage tank needs advanced insulation, specialized pumps, and constant pressure management. Heat entering the tank can cause some of the liquid hydrogen to evaporate. This makes liquid hydrogen more suitable for specialized transport and industrial applications than ordinary passenger vehicles. The third method is solid hydrogen storage. Certain materials can absorb hydrogen and hold it inside their chemical structure. Magnesium hydride is one of the best known examples. Instead of keeping all the hydrogen as a highly compressed gas, the system stores it inside a solid material. That can improve density and reduce dependence on extremely high-pressure storage. But magnesium hydride holds hydrogen tightly. Releasing it through ordinary heating methods can require between 300 and 400 degrees Celsius. That is the barrier Japan has started to remove. The Japanese battery uses electrical control to move hydrogen into and out of magnesium. The hydrogen travels through a solid electrolyte as hydride ions. This allows magnesium hydride to form during discharge and separate during charging at approximately 90 degrees Celsius. The reaction still requires thermal management, but moving from temperatures approaching 400 degrees to around 90 degrees changes the engineering possibilities. A future system could use waste heat from a fuel cell, motor, or industrial machine to help maintain the required operating temperature. Insulation could keep the active material warm during operation. Electric heating could prepare the system during startup. Further improvements to the electrolyte could push the reaction temperature even lower. Japan has therefore attacked the most difficult part of solid hydrogen storage, releasing and recovering hydrogen without relying on extreme heat. How it could power an electric vehicle. A hydrogen fuel cell vehicle is already a form of electric vehicle. The difference is where the electricity comes from. A battery electric vehicle stores nearly all its usable energy inside a large battery pack. A hydrogen fuel cell vehicle stores hydrogen in tanks and converts that hydrogen into electricity while driving. The fuel cell combines hydrogen with oxygen from the air. This produces electricity, water, and heat. The electricity travels to the electric motor, which turns the wheels. A smaller battery is normally included to capture braking energy and provide additional power during acceleration. Japan's magnesium-hydrogen battery could create several new system designs. The first design would use the magnesium-based material as a solid hydrogen storage unit. Hydrogen released from the battery could feed a fuel cell stack. This could reduce the amount of hydrogen that must be stored only as extremely high-pressure gas. The second design would use the magnesium-hydrogen reaction to produce electrical energy more directly. The cell itself already generates current while magnesium hydride forms. The third option would combine both functions. The battery could deliver electricity during certain operating conditions while also supplying hydrogen to a fuel cell during longer or heavier demand. That could give the vehicle several energy sources inside one connected system. Engineers would still need to build the thermal controls, power electronics, hydrogen management system, and safety structure. But the Japanese cell provides the central electrochemical mechanism. The same idea could also be used outside passenger cars. A delivery truck could use magnesium-hydrogen modules to reduce its dependence on enormous lithium battery packs. A train could store hydrogen inside protected solid units and use fuel cells to generate electricity across long routes. A bus could refill or replace hydrogen storage modules at a central bus depot. A factory could use the battery to store hydrogen produced from excess renewable electricity. The technology becomes especially valuable where vehicles return to the same location repeatedly. Instead of building thousands of public hydrogen stations immediately, operators could install hydrogen infrastructure at bus depots, ports, mines, warehouses, and freight centers. That is already how many hydrogen transport projects are being developed. Hydrogen cars already operating. Japan has been developing hydrogen vehicles for decades. The Toyota Mirai was launched in 2014. The Mirai is a fuel cell electric vehicle. Compressed hydrogen enters the fuel cell system, where it reacts with oxygen to create electricity. That electricity powers the vehicle's electric motor. The Mirai demonstrated that a hydrogen passenger car could offer long driving range and refuel within a few minutes. Toyota later introduced a second generation with a redesigned platform, greater range, and improved performance. The company has also developed a third-generation fuel cell system for future passenger and commercial vehicles. The new system is designed to improve durability while reducing production cost. Honda has taken a hybrid approach. The Honda CR-V EF-CEV combines a hydrogen fuel cell system with a plug-in battery. The driver can charge the vehicle from the electrical grid for shorter journeys. Hydrogen can then provide additional range for longer travel. This design shows how hydrogen and battery technology can work together instead of competing directly. Hyundai has also continued developing hydrogen passenger vehicles. The Hyundai Nexo uses a fuel cell electric system and provides the long range and quick refueling associated with hydrogen transport. South Korea has supported hydrogen stations, buses, trucks, and passenger vehicles as part of its broader energy strategy. These cars prove that hydrogen electric transportation already works. The main barriers are price, hydrogen availability, and infrastructure. Current fuel cell vehicles require expensive tanks and complex fuel cell systems. The hydrogen itself must also be produced, transported, and sold at a competitive price. Japan's magnesium-hydrogen battery could reduce one part of that cost by improving the storage system. It could also make hybrid hydrogen battery designs more practical. But passenger cars are not the only market. Hydrogen becomes even more valuable as vehicles grow larger. Large trucks require far more energy than small passenger cars. A battery electric truck can carry a very large lithium pack, but every additional battery module adds weight. That reduces the amount of cargo the truck can carry. Charging an enormous truck battery can also require powerful electrical connections and long waiting periods. Hydrogen provides another solution. A fuel cell truck can carry hydrogen, convert it into electricity, and use electric motors to move the vehicle. Refueling can take far less time than charging an extremely large battery. Toyota, Hyundai, Honda, and several commercial vehicle manufacturers are developing hydrogen truck systems. Hyundai has already deployed Xcient fuel cell trucks in commercial operations. Toyota has tested fuel cell powertrains in heavy trucks and developed systems intended for long-distance commercial use. Ports are especially suitable for hydrogen trucks. The vehicles operate along planned routes. They return to central locations. They carry heavy loads, and refueling equipment can be installed inside the port rather than across an entire country. Hydrogen buses work in a similar way. A city bus returns to its depot at the end of the day. The depot can refuel many buses from one hydrogen station. The buses can then travel long routes without carrying extremely large battery packs or stopping for long charging periods. Hydrogen buses have operated in Japan, South Korea, China, and several European countries. Warehouse vehicles provide another successful example. Fuel cell forklifts can refuel quickly and operate across long shifts. A lithium battery forklift may need time to charge or require battery swapping. A hydrogen forklift can return to work soon after refueling. These heavy and repetitive uses are likely to adopt advanced hydrogen storage systems before ordinary passenger cars. They can accept larger equipment. They operate from controlled facilities. And the financial value of reducing downtime is much greater. Once production increases in these markets, the technology can become smaller and cheaper. Industrial use creates scale. Scale reduces cost. Lower cost allows wider adoption. Hydrogen trains and ships. Hydrogen is also moving into rail transport. Many railway lines around the world are not connected to overhead electrical wires. Electrifying every kilometer of track can be extremely expensive. Diesel trains are often used instead. Hydrogen fuel cell trains provide a third option. The Alstom-Coradia I-Lint became the world's first hydrogen fuel cell passenger train to enter regular service in Germany. The train carries hydrogen, generates electricity through fuel cells, and powers electric traction motors. Its only direct operating emissions are water and heat. During a long-distance demonstration, a Coradia I-Lint traveled more than 1,100 kilometers without refueling. The manufacturer Stadler later achieved an even greater demonstration with its Stadler Flirt H2 train, traveling more than 2,800 kilometers without refueling or recharging. These demonstrations show why hydrogen is attractive for railway systems. A train can carry enough hydrogen for long operation, then refill at a depot or major station. Japan is also developing hydrogen trains. JR East, Hitachi and Toyota have worked together on a hybrid rail vehicle combining hydrogen fuel cells and storage batteries. The fuel cell generates electricity from hydrogen. The battery captures braking energy and supports the train during acceleration. Ships create an even larger opportunity. Large vessels require huge amounts of energy. Battery power can work well for short ferry routes, but long-distance shipping requires energy storage on a much greater scale. Kawasaki Heavy Industries developed the Suiso Frontier, a ship designed to transport liquefied hydrogen. The vessel demonstrated the movement of hydrogen between Australia and Japan. Future hydrogen carriers are expected to transport much larger quantities. Hydrogen and hydrogen-based fuels are also being developed for ferries, cargo ships, and port equipment. A magnesium-hydrogen battery could support these systems by providing controlled solid storage, onboard electricity, or a buffer between hydrogen tanks and fuel cells. The same core technology could therefore reach cars, trucks, buses, trains, ships, and energy storage facilities. This explains why Japan is investing so heavily in hydrogen. Japan's national hydrogen strategy. Japan has limited domestic fossil fuel resources. The country imports large amounts of oil, coal, and natural gas. That makes energy security a major national priority. Hydrogen gives Japan another method of importing and storing energy. It can be produced using renewable electricity, natural gas with carbon capture, nuclear power, or industrial processes. It can then be transported as compressed hydrogen, liquid hydrogen, ammonia, or other hydrogen-carrying materials. Japan introduced its first basic hydrogen strategy in 2017 and later expanded it. The national plan targets large increases in hydrogen and ammonia use over the coming decades. Government and industry investment is directed toward hydrogen production, international supply chains, fuel cells, transport, power generation, and industrial use. Toyota develops vehicles and fuel cell modules. Honda develops fuel cell systems and plug-in hydrogen vehicles. Kawasaki works on liquefied hydrogen transport. Japanese railway companies are testing hydrogen trains. Japanese researchers are creating new solid electrolytes and hydrogen storage materials. The magnesium-hydrogen battery fits directly into this strategy. It provides a new method for connecting hydrogen storage with electrical output. Japan is building multiple parts of a hydrogen economy at the same time. That creates a powerful advantage. A battery breakthrough becomes more valuable when vehicle manufacturers, fuel cell suppliers, infrastructure companies, and government programs are prepared to use it. The next challenge is cost. Japan can develop the technology, but China has built the world's most powerful system for reducing the cost of electric vehicles. That is why China's reaction matters. Why China is shocked. China dominates the modern battery industry. It manufactures more than 80% of the world's battery cells. It also controls approximately 85% of cathode production and more than 90% of anode production. Chinese companies lead the production of lithium iron phosphate batteries used in many affordable electric vehicles. CATL is the world's largest EV battery manufacturer. BYD manufactures both batteries and complete electric cars. This gives China control across the supply chain. Raw materials move into chemical processing. Processed materials move into battery factories. Battery cells move into vehicle plants. Finished electric cars then reach the market at extremely competitive prices. Japan's magnesium-hydrogen battery challenges the assumption that every future EV must depend on that same chain. The battery uses hydrogen ions instead of lithium ions. Its main storage material is magnesium hydride. Its solid electrolyte is built from another group of materials. If the technology reaches large-scale production, manufacturers will need different factories, suppliers, and engineering knowledge. That creates an opening outside China's strongest lithium advantage. China's reaction is visible in the speed of its own research. Chinese scientists published an all-solid-state hydride ion battery using a specialized core shell electrolyte. The cell moved hydrogen ions through a solid material and operated under far milder conditions than many earlier hydride systems. Chinese researchers then produced a magnesium-hydrogen gas-solid battery, closely connected to the same direction demonstrated by Japan. The Chinese prototype used magnesium, hydrogen gas, and a hydride ion electrolyte. It achieved an initial capacity of approximately 1,526 milliamp-hours per gram. It retained more than 70% of its capacity after 60 cycles. It also operated across temperatures ranging from approximately -20 to 90 degrees Celsius. Researchers connected 10 cells into a stack capable of lighting an LED. Japan achieved the higher active material capacity. China demonstrated wider temperature operation, more cycling data, and a multi-cell stack. This is now a direct technology race. Japan established a lithium-free magnesium-hydrogen battery with full theoretical capacity. China moved quickly into a similar gas-solid system and began extending its operating range. China understands the importance of the chemistry. A successful hydrogen battery creates another route into electric transportation, and China has no intention of allowing Japan to control that route alone. How China could make hydrogen cars extremely cheap. China already produces some of the cheapest electric vehicles in the world. The Wuling Hongguang Mini EV entered the Chinese market at a price far below most electric cars sold in Europe or the United States. Other Chinese manufacturers now offer small electric vehicles in similarly low price categories. These cars are inexpensive because Chinese companies control nearly every part of production. Battery suppliers are located close to vehicle factories. Platforms are shared across different models. Factories operate at enormous scale. Competition forces manufacturers to reduce prices constantly. Vehicles are designed around what customers actually need instead of adding expensive equipment to every model. China could apply the same system to hydrogen EVs. The first step is improving the battery. The operating temperature must fall. The solid electrolyte must become cheaper. The cell must survive hundreds and eventually thousands of cycles. The complete system must deliver enough power for acceleration and continuous driving. The next step is reducing the cost of the fuel cell. Fuel cells use specialized membranes, catalysts, and control equipment. Toyota, Honda, Hyundai, and Chinese manufacturers are already working to reduce these costs. The third step is lowering the cost of hydrogen storage and refueling. A magnesium-hydrogen battery could reduce reliance on extremely large 700-bar tanks. Solid storage could also improve safety and simplify transportation in certain applications. The fourth step is mass production. Once China standardizes the cells, modules, fuel cell stacks, motors, and control systems, prices could fall quickly. The first commercial vehicles will probably be trucks, buses, trains, delivery vans, or industrial machines. These vehicles operate from fixed depots and can support central hydrogen infrastructure. After production expands, smaller vehicles can follow. A Chinese manufacturer could then combine a compact hydrogen storage system with a small fuel cell, an electric motor, and a basic city car platform. That is how a future hydrogen EV could begin approaching the price of China's cheapest electric cars. A vehicle near $6,000 would require major cost reductions. But China has already shown how quickly expensive clean technology can become affordable once factories reach enormous scale. Solar panels followed this path. Lithium batteries followed this path. Electric vehicles are following it now. Hydrogen batteries could be next. Japan has developed the breakthrough chemistry. China is developing its own version, and Chinese mass production could eventually turn the technology into something far cheaper than today's hydrogen vehicles. Japan has built a rechargeable hydrogen battery that removes lithium from the center of the reaction. The cell uses magnesium, hydrogen gas, and a solid hydride ion electrolyte. It reached approximately 2030 milliamp-hours per gram, matching the full theoretical capacity of magnesium hydride. It stored approximately 7.6% hydrogen by weight inside the active material, and it performed the reversible magnesium-hydrogen reaction at approximately 90 degrees Celsius, far below the extreme temperatures traditionally required. This gives Japan a real lithium-free route into the future EV industry. The same chemistry can connect battery storage, hydrogen storage, and electrical power. It can support passenger cars, heavy trucks, buses, trains, ships, and industrial energy systems. Japan already has Toyota, Honda, Kawasaki, national hydrogen investment, and decades of fuel cell experience behind it. But China has already responded. Chinese researchers developed their own solid hydride ion battery. They then built a magnesium-hydrogen gas solid cell operating across a wide temperature range. Japan reached the stronger capacity result. China began demonstrating cycling, stacked cells, and broader operating conditions. The competition is now moving quickly. Japan has opened a route outside the lithium supply chain. China dominates. China is now working to master that route before Japan can control it. And the final battle will not be decided by one laboratory number. It will be decided by cost, safety, temperature, battery life, vehicle integration, and manufacturing scale. Japan currently holds one of the most important hydrogen battery breakthroughs. China holds the world's strongest low-cost EV manufacturing system. If Japan turns the chemistry into a complete vehicle first, it could lead the next stage of hydrogen transportation. If China learns how to manufacture the system faster and cheaper, hydrogen EVs could fall into price ranges that seem impossible today. That is why this battery matters. Japan has built an electric energy system where hydrogen moves, magnesium stores it, and lithium is no longer essential. China has seen the same opening, and now both countries are racing toward the same result: a hydrogen electric vehicle that can travel far, refuel quickly, and eventually cost as little as the cheapest electric cars on the road. Subscribe